In this video, we are going to talk about some of the applications of redox reaction. Specifically, we are going to talk about galvanic cells and some of the terminologies associated with galvanic cells, such as half cells and salt bridge. We will also be discussing which electrode should you choose for the galvanic cell you have set up. We will end our video with an introduction of electrochemical theories for predicting which reaction would occur, as well as doing some practice questions. So let's begin by doing some recap of redox reaction. So essentially what redox reaction is, it's basically transfer of electrons. So this is the fundamental idea behind redox reaction. It's basically separated into reduction reaction, which is involved of gaining of electron, and simultaneously oxidation reaction, which is losing electrons. The two reactions must occur simultaneously. Hence, the reason why we put the reduction and oxidation together in the same word. So as we have introduced before, combustion is also an example of redox reaction. But how do you generate electricity using combustion reaction? It's not actually through the transference of electrons. It's through combustion of the fuel itself to heat up water and then use the water vapor to spin the turbine and then generate electricity. So this exposes one problem with the redox reaction. So if the redox reaction occur at the same container or occur at the same place, there's no transfer of electron and thus no electric current. But if we can separate the two half equations, so the oxidation and reduction reaction, if we can somehow separate those two half equations into different containers, then something magical would happen. So electrons will be forced to move between the containers. And the movement of electron is precisely what electric current is. So this is how we generate electricity from redox reaction. It's by separating the two half equations into different places and force the electron to move between the containers. So specifically, electron would move away from the site of oxidation. Remember, oxidation is losing electron, and move towards the site of reduction, which is the gaining of electrons. So we can exploit this characteristic of redox reaction by using something called galvanic cell. So this is the oldest type of battery. We will be covering battery and fuel cells in subsequent videos, but the underlying principle is the same as galvanic cell. So you should be very comfortable with this concept before moving on to the study of batteries and fuel cells. So a galvanic cell looks indeed like two containers. So it can be two beakers, and we need electrodes. We also need a wire. So this is electrodes. We also need a wire to conduct electricity. We will also need some kind of ionic solution. And we also need a salt bridge. And salt bridge is very important, as we will discuss later. So each of this container is called a half cell. The reason why we call them half cell is because half of the equation occurs, or half of the complete chemical reaction occurs in this one particular cell. Maybe this one of the cell is conducting oxidation. One of the cell is doing reduction. So that's why it's called a half cell. In particular, a half cell contains electrode in ionic solution. We will talk about the choice of electrode later, but one most very important fact is in each half cell, we need a conjugate redox pair. So what is a conjugate redox pair? If you go to your chemistry data book, you would see this thing comes up first. And everything here is a conjugate redox pair. For example, the zinc ion and the zinc metal. These two things are its conjugate redox pair. The copper ion, copper metal, they are conjugate redox pair. The hydrogen ion and hydrogen gas, they are also conjugate redox pair. So this is what I mean by conjugate redox pair. So maybe we can use the zinc as an example in our illustration. So an example of conjugate redox pair is the zinc ion and the zinc metal. So maybe for this particular half cell, we can make the solution to be something containing the zinc ion. And we can make the electrode zinc metal, because it is a very natural choice, since the conjugate redox pair actually involves metal. If we have something like the example of hydrogen gas and hydrogen ion, this would be impossible, since both hydrogen ion and hydrogen gas, they are not metal. So in this case, we are going to choose something different, and we will talk about the choice very soon. So why do we choose a conjugate redox pair? So for this ionic solution, in theory, I can choose many different things. Maybe I can use copper ion. Why do I choose the zinc ion as the thing containing in my solution? It is because we don't want secondary reaction from occurring. If you have copper ion, maybe it would react with other chemicals. And this is very undesirable. So to minimize the risk, we are going to use the conjugate redox pair. So this is always the safest choice. And that's why we are choosing using the zinc ion in our solution. You can also use different things. but there's always a risk there you are taking. So it's better not to take the risk. That's why we use the conjugate redox pair. And also we know that because we have ionic solution, we need to have cations and ions. So what should you choose for the negative ion? Usually you choose you need to choose something soluble. So from year 11 chemistry, you know that things like nitrate is usually soluble. So this is a very good choice. So maybe for the solution, we can actually use zinc nitrate. And zinc nitrate is soluble in water. So why do we want to choose something soluble? It's because we want to prevent precipitation. So if you use some negative ions and forms a solid with your positive ion, then the whole reaction will broken down. So all of this will turn into a solid, and then your galvanic cell will not work. We need to choose something soluble. And this ion, the nitrate ion, is a very safe bet for you. So in the exam, I recommend always using this ion as your negative ion. So it is always safe. If you choose something very fancy, maybe it would actually form precipitation with some metal cations. And if that's the case, your whole galvanic cell would not work. So your answer would be incorrect. And you will lose a mark as a result. So now let's move on to the choice of electrodes. So as we have discussed before, so if the conjugate pair happens to be a metal, such as in this example, we just use the metal as the electrode. And if there is no metal, in the conjugate pair, for example, these two species, then we need to choose something different. We can't use active electrodes like zinc or copper electrodes because they may want to participate in the chemical reaction, which we do not want. We only want these two things to be involved in the half-cell reaction. We don't want to introduce any unwanted substance. Maybe they will not react, but maybe they will. So you are actually taking some risk here. And we do not like taking on risk, especially in the exam. So that's why we need to use something called inert electrodes. A very good example of inert electrode is graphite. Graphite is basically carbon. We know that carbon is very inactive. And in fact, if you look at the electrochemical series, you can't see carbon here. So that's why carbon is a good choice. It wouldn't participate in any unwanted secondary reactions. You can also use gold as your electrode. But the reason why we do not want to use gold is because it is too expensive. Gold is actually a good conductor of electricity as well. But compared to graphite, it is so much more expensive. So aside from the chemical properties, you should also consider the financial viability of choosing some particular electrode. So in this case, gold is actually a very good candidate, but because of its price, we should choose graphite instead. Sometimes they do ask you this kind of question in the exam. Like why shouldn't we choose gold as the electrode? Then your reasoning should be based on the financial side rather than on the chemical properties of gold. So from your knowledge of a battery, you know that one side of the battery has positive terminal and another side of the battery has negative terminal. You have positive terminal and negative terminal. But what makes them positive or negative? So if you are doing oxidation, you are losing electrons. Remember, oxidation reaction looks like this. So you want to reject electrons. You need to somehow get rid of this electron. And that's why zinc is called the reducing agent. So it wants to give its electrons to other chemical species. In any case, it is losing electrons. So we know that something with the same charge would repel. So if you have something negatively charged, it would repel electrons. And that's why the site where oxidation occurs is the negative terminal. Because electrons exit this oxidation site. And the fact that electron leaves this site means it is negative. Because same charge repel each other. And the site of oxidation is called anode. In the next section, we will explain why this is called anode. For reduction, we know that it's gaining electrons. So opposite attracts. This means when something attracts something negative, it must be positively charged. So the site of reduction is the positive terminal. It is called cathode. There are some ways to remember this. So anox means anode is oxidation, and red cat, reduction is cathode. So that's some of the ways you can remember this. But I think the best way to remember something is to try to understand it. So that's why we need to have a knowledge of salt bridge. So remember, in our previous drawing, we actually have a salt bridge. And this is actually really important. Without the salt bridge, your whole galvanic cell would not work. So the function of salt bridge is to balance the charge. So why do we need to balance the charge? So maybe first let's look at one example. if I tell you these two reactions would occur, we will also get to the reason why these two reactions would occur in the next section. And maybe let's draw a quick sketch of the galvanic cell. So because if we look at the conjugate, we actually have a metal here. And if we look at this conjugate, we also have a metal here. So that's good. So we can use them as the electrode, as we have discussed the reason before. And we also need an ionic solution. And we also want to choose the redox conjugate because it reduces the chance of secondary reactions, which means we are very safe. We do not want to take any risk. We also said the nitrate salts are very, very soluble. So it wouldn't form any precipitation. So would reduce our risk further. So we choose this ionic salt. And for copper, we use the same choice again. Of course, we need the salt bridge. And we know that, since I have already told you that zinc is getting oxidized, so the electron would move from the zinc terminal and into the copper terminal. So this is the direction of electron flow. And since the zinc terminal is rejecting electrons, it is negatively charged. And since opposite attracts, if the electron is attracted to the copper terminal, it is positively charged. So this is what our galvanic cell looks like. Also, over time, the zinc electrode would corrode away because zinc had been turned into zinc ion, which is soluble and dissolved in the solution. And we would actually see some deposits, copper deposit, around the copper electrode. Because we know the copper ion have actually been turned into copper metal from this half equation. So a problem immediately occurred. Since zinc metal has been turned into zinc ion, which is positively charged, we have a buildup of positive charge on our, remember what is the name of this? We are undergoing oxidation here, so it is called anode. And also, since the copper ion turns into copper metal, there is a buildup of negative charge. Because all the copper 2+ ion in the solution have been turned into copper metal. So you only have this negative nitrate ion in the solution. So that's why you have more and more and more nitrate ion flowing around. So you have a lot of negative charge. So overall, you have unbalanced charge. And if this is the case, your reaction would stop very, very soon. And you have no electric current generated. So the whole reaction would stop. So what is your solution to this problem? You use a salt bridge. So a salt bridge is usually a piece of paper soaked in salt solution or ionic solution, consisting of highly soluble ion. This is key. We don't want any precipitation from forming, because whenever precipitate forms, it would no longer act as a salt bridge. So the idea of salt bridge, usually we want something like potassium nitrate or sodium nitrate. So all of those are soluble. In fact, highly soluble. So that's always the safe choice. So the idea is, because you have build-up of positive charge on the anode, the salt bridge transfers or gives negative charge to balance the charge. So what is the negative ion? Nitrate. The nitrate ion enters this half cell via the salt bridge. And because you have build up of positive charge, and then the negative ion flows into this side of the half cell, the charge is balanced, and you can have your reaction continue going. And what is negative ion called? It is called anion. And that's why this is called anode, because negative anions flows to anode. So in summary, so that's why it is called anode. Similarly, if you have a buildup of negative charge, so potassium ion or sodium ion move to, remember what is this site called? Site of reduction is called cathode. Moves to cathode. So you have lots of negative charge, so the positively charged ions move to cathode to balance the charge. And what is positive ion called? They are called cations. So cations goes to cathode. So that's why we have the name anode and cathode. And this is the purpose of the salt bridge. So now perhaps So now let's investigate, why does this two reaction occur? So why does zinc turns to zinc ion and copper ion turns to copper? Why not the other way around? To answer this question, we need to use electrochemical theories. And electrochemical theories is particularly important, very, very, very important. And the way you can tell it is important is because it is the first thing that comes up in your VCE Chemistry data book. So there must a reason for it, and this is the reason. You can use electrochemical theories to predict which reaction will occur. So let's have a look of some of the characteristics of the electrochemical theories. So as you can see, all half equations are written as reduction half equation. So everything is actually gaining electron here. So this makes it easy to see. So if you have some as the reduction half equation, some as the oxidation half equation, everything would look very messy. So you must make a choice. You either write everything in terms of the reduction half equation, or write everything as the oxidation half equation. In this case, we have chosen to write everything as the reduction half equation. So this is not a problem, it's just a convention. And it contains conjugate redox pair. So everything here are conjugate redox pair. So this is good to know. The most important thing you can see from or obtain from the electrochemical theories is that at top left, it is the strongest oxidation agent. Remember, oxidation agent causes other species to undergo oxidation, so itself is reduced. So I would call this something that loves electron. So it really wants to undergo reduction. So where is top left? So here is top left. So actually, it is the fluorine gas that is the strongest oxidation agent. Really wants to gain electrons to become fluoride ion. So the fluorine gas is very reactive. It really wants to gain electron, really wants to turn into fluoride ion. On the other hand, the fluoride ion is not very reactive because it really wants to stay as the fluoride ion. So it really wants to stay in the state where it gained the electron. So if you want to turn the fluoride ion into fluorine gas, very, very difficult. And to turn from fluorine gas into fluoride ion, really, really easy. So that's another insight you can get from looking at the electrochemical series. So everything actually has an opposite story. If its original form really wants to become the reduced form, then the reduced form really don't want to lose electron anymore. Very interesting thing to note. So conversely, the opposite of top is bottom. The opposite of left is right. So the bottom right is actually the strongest reducing agent. So really hates electron, really wants to become oxidized. So really want others to be reduced so it can lose its electron. So let's look at bottom right. Lithium. The reason you don't see lithium metal occurs as a natural element is because it is very reactive. It really wants to become lithium ion. So it really wants to go in this direction. It really wants to lose the electron to stay in the ion form. And conversely, the lithium ion is very stable. So it really don't want to gain electron to return back to lithium. So lithium ion is very unreactive, but lithium solid is very reactive. It would react vigorously with air. So that's how reactive it is. So based on our reasoning, because lithium is the strongest reducing agent, then the converse is also true. The lithium ion is the weakest oxidizing agent. Remember, oxidizing agent undergoes reduction, so it really doesn't want to gain electrons. Conversely, since fluorine gas is the strongest oxidizing agent, the fluoride ion is the weakest reducing agent. Remember, reducing agent undergoes oxidation itself. It really doesn't want to go oxidation. It really wants to stay as fluoride ion. So that's how you read, use, and understand electrochemical series. So now let's have a look and have a think further. If you have something like copper ion present in your system, and you also have zinc present in the system, would they react? And which way would the reaction go? Actually, you also have all the conjugate pairs in your galvanic cell as well. So we want to know which would be oxidized, which would be reduced. So to answer this question, let's first look at this, which will be oxidized. So the answer to this question, or we can ask this question in a different way. So who is the strongest reducing agent? Remember, the bottom right contains the strongest reducing agent. So let's look at who is on the bottom right. Bottom right. So we look at everything here. So looks like zinc is the most bottom right chemical we have in our system. And hence, it's zinc metal. And who will be reduced? In other words, who is the strongest oxidation agent? Remember, oxidation agent, we look at the top left. We move to the top left. So we look at here. So the first thing we get is the copper ion. Then the answer to our question is, it is the copper ion. So copper ion would be reduced. Copper ion will be reduced. So it goes in this direction. Zinc metal will be oxidized. It goes in this direction, which is exactly the same result as what I have told you. Zinc will be oxidized, copper will be reduced. So this is good. To save your time, I would also review one more fact. Maybe you have already observed this. Because for the oxidation agent, we are looking at the left-hand side. So this implies anything on the right-hand side, so anything here, they would never be reduced. Makes sense, right? You cannot add electrons to a metal and making a metal negatively charged. You've never seen those kind of things before, so it never can be reduced. So metals can never be oxidation agent. Only the metal ions can be oxidizing agent. So only the ions can undergo reduction to gain electrons to become metal. And conversely, those metal ions can never be oxidized. So you cannot make zinc ion to lose any more electrons. Otherwise, it will be unstable. So that's another thing you can tell from the electrochemical series. So how do you predict the reaction? You can look at this graphically. So if you have copper and zinc present in your system, and you connect a line between them, and if this line is negatively sloped, the reaction would occur, and copper ion will become copper, zinc will become zinc ion. Conversely, if you only got the fluoride ion and iodine solid in your system, and then you try to draw a line between them, you get this positively sloped line. In this case, nothing would happen. You can also perhaps try to understand this using the chemical theory. Because the fluoride ion, as we discussed here, is the weakest reducing agent. Of course, it cannot undergo a reaction. If you look at the conjugate pair, this is actually a stronger reducing agent than the fluoride ion. So which means if you force this reaction to occur, it would naturally immediately turn back to its original form. So the system is unstable. It cannot stay. So imagine you force this to force the reaction to complete. And because you get a negatively sloped line, immediately they will turn back to its original form. So the reaction in this case would not occur. Only if you have a negatively sloped line. So even if you have copper solid and then zinc ion in your system, you get a positively sloped line. So these two things will not react, and your system is stable. You do not get any more reactions going on. So the reaction would gradually complete. So another thing I want to emphasize, or I want to mention, is this potential difference stuff. So everything here is relative. Relative to whom? Relative to this particular reaction. The way you set up this experiment is you have two cells. And the first cell is always fixed. So in this case, you get the hydrogen ion and you feed hydrogen gas into this confined space. Because you don't have any metal as your conjugate pair, you use the graphite as inert electrode. So everything is relative to this standard hydrogen cell. Of course, you have the salt bridge. And here, for this cell, it's whatever metal or conjugate pair you are testing. Maybe we use the zinc example again. So the salt bridge, you have something very soluble. You can do KOH, or you can do potassium nitrate, doesn't matter. And you put a voltmeter here. And then you look at the readings on this voltmeter. All the experiment is conducted under standard condition. So by standard condition, I mean 100 kilopascal, 25 degrees, 1 molar concentration of all ionic solution. So everything is conducted under this environment. If anything, if the air pressure or temperature or concentration is different, you get a different reading. So if you actually do this experiment yourself, you would see a voltage of negative 0.76 on your voltmeter. And because of this negative, you know that zinc is the negative electrode, and this is the positive electrode. And you can actually write the chemical reaction equation. We know that zinc turns into zinc 2 plus 2 electrons by just copying directly from the electrochemical series. And looking at here, we can also copy it down directly. We know that the hydrogen ion, look at the relative position. So the hydrogen ion actually turns to hydrogen gas. So we copy down this chemical reaction from the electrochemical series. And we just add those two equations together. And the electrons cancel out. So this is the overall equation of this chemical reaction. And the voltage here is the maximum theoretical voltage you can obtain from this reaction. If you drew a different cell, for example, if you do between fluorine gas and lithium, you get a negatively sloped line, so the reaction would occur. Fluorine gas would be reduced, lithium would be oxidized. So what is the theoretical voltage of this galvanic cell? You just take the difference between the two. So 2.87, the difference minus negative 3.04. You get 5.91 volt. So this is the theoretical voltage, the theoretical maximum voltage of this particular galvanic cell. And the anode would be the lithium anode, and the cathode would be here. So let's end this video with some practice questions. For those chemical species, would a reaction occur or not? Let's have a look. Zinc 2 plus and copper. Copper is here. Zinc 2 plus is here. To form a positively sloped line. So the reaction would not occur. Hydrogen ion and cobalt. Let's have a look. Hydrogen ion is here. We look at where CO is here. So a negatively sloped line. The reaction would occur. Nickel 2 plus and magnesium. Nickel 2 plus, magnesium. A negatively sloped line. Reaction would occur. Lastly, let's look at zinc and magnesium ion. Zinc. and magnesium ion, a positively sloped line, so the reaction would not occur. So this is how you solve questions associated with the electrochemical series. But I think the key theory is here. Try to really understand what is going on, and also try to understand why the converse is also true, based on what I have said, the relative stability between the conjugate pairs. In the next video, we are going to talk about electrolysis.